In this example, I want to add the content of the D with the C index I. So I assume that the I is inside one variable, one register. For example, sign 19. I should first multiply by 4, then add it to the start address of the C, which is inside a sign 10. In order to multiply a variable by 4, you can add it 2 times with itself. So if I add I by I, it will be 2i. Then if I add 2i with 2i, the answer will be 4. So in order to compute 4 times I will write it in this way. Whereas the I and I will be add together and I save it in some register. Then this is 2i, the 2i and the other 2i will add together. So we have 4i. Now I can save it in any register that I want. So inside I have 4 times I should be at with the bases in the $10. So for I plus base with the address of the C index, I keep it in sign 11. And as you can see by load word, we don't have any offset here because I compute the address completely. And it is inside $11. So the offset is 0 and this is the real C indexed I address. I load it and store it in the registers 12 and finally I add it with register 13, which is assumed that the content of the B is here, and we store another register which is corresponding to the A variable. So this is the way that we can find the office of the C index I. Instead of multiply by 4, I add 2 times 5 with itself. First a computer to AI and then to AI. Plus 2. I will be for I. Then this fall I will be at the base and the fortress is completely computer. So the offset is 0 and this base is really just after seeing this slide. We have multiply instruction in MIPS, but I will cover it with another lecture. Of course we're finding 4 times I. It is better to perform these 2 additions instead of 1 multiplication, because the multiplication takes more time of the CPU than the addition. So 2 additions is faster than 1 multiplication. It's depend on the way that they implement the multiplication algorithm. But for the multiplication by 4 it is better to use shift selection first, then addition is faster than the real multiplication. If you talk about the shift in instruction, the speech, the storing data. I talk about this in a selection last week. It is similar to the load, but this time this value will be stored in this address. So the offset will be at the base and this is the address of the memory location that we want to store the content of this register. So I have one value. I want to store it in an index. I again assume that I is inside one register, so I will multiply I by 4 by 2 times. Added is inside. Is there 9 here? So now a register 8 is 2i, then 2 plus 2i will be 4i and I store it in the register 8. So register 8 is now 4 times I in the add with the start of this of the A, which is in dollars and 7. So this is the base plus the I times 4 and I store it somewhere. Now the result that I computed here, the plus C in the $16 will be stored in the boxes that is computed by adding that sum 10 content with nothing with 0 offset. Let's talk about the Little Indian on Big India. Last week I also told you that the bytes would be multiplied by 4. but this off the wall should be multiplied by 4. So this is the meaning of a line in the memory. So one word should be stored at 0 for a 12, 16, or another number, which is the multiplies of 4. Some pictures of the assembler by default. The number that you mentioned in the assembly will be considered as the base of 10. If you want to mention the number in hexadecimal, 4 weeks in the beginning and then the digits can be written in hexadecimal for 0, X, F, F in the hexadecimal. Later, followed by colon. Keyboards cannot be used as the identifier. Of course it cannot split one in a selection in across multiple lines. If you see language, you can mention one line of the code. For example, if parenthesis, then the condition here, then close parenthesis here. But in the assembly you have to write one in one line. Another important type of instructions are flow control instruction in the program that you write will be executed line by line. But of course we want to write a program with some control following instructions. We want to implement, if-else, structure, loop and other repetitive instructions. Let's see what will be the equivalent of these instructions in assembly. There are two different types of changing control instructions known as branches and jumps. Branches are the conditional instructions. First we check a condition, and if that condition is true, then the control flow to another part of the program. But in the unconditional situation, we have another type of instruction that allowed us to jump. The first conditional branch is the equality branch equal is the upper the equal. But as you can see, there are three parameters or plant. The content of this register will be checked together. If they are equal, then the control flow will be jumped or go to this label. So this is another part of the program that you assign a label to that line, and we want to jump to that location and continue the code that are written in that location. So this is a conditional jump. Has the quality of the register 1 and 2. If it is true, if both of them have the same value, then the control will be moved to a line that I assign this label. For example, check this out, which is written in C language where we never use goto in the C, but there is a goto instruction in the C which can help us to move to a specific line of the code. And in the C, also you can assign label to some part of your code. But as I mentioned, we never use goto in the C. However, because exist in the program, this is one of the basic idea of the structural programming. Never use goto in your code because then you cannot be reused. I think that this is the instruction A is equal to the B. The value of the A and B are equal. Then we want to jump to the end one, which is another line of the code. Maybe it is upper than the 5th or 10 lines after the if, and if it is not equal, then the compiler will be continuing with the next statement. So this is the code segment that I want to convert it into the needs. So this is the equivalent code in the MIPS branch. Assume that the A and B are inside sign 19 and 20 registers. If these two registers are equal, then jump to the L1. And there are some instructions here. But if they are not equal, then this part will be executed. Do something. Another branch instruction is branch, not equal. If two registers are not equal, then we will jump to the label. And one conditional job, the DJ instruction job to the label. There is one apparent only jump to label, so this is unconditional. When the CPU reach to this instruction, it is almost to the line with this label. But for this instruction, branch not equal or branch equal, it is conditional jump. First, the condition will be checked. If it is satisfied, then we will move to the L1. Otherwise we will continue with the next instruction, like the other instruction that we execute. We always move to the next and the selection can be executed. One in a section. We will go to the next one. Only we will jump to another part of the code if some branch will be happy or some jump executed. Okay, check this. If, for example, in this flowchart you can see the condition y is equal to the j. There are two possibilities. True or false. If it is true, we want to perform this operations and then go to the remaining part of the code or exit part of the code. And if they are not equal, then we want to perform this operation and then we will come to this point. So one of these two statements should be executed according to the relation between all. If they are equal, f is equal. Otherwise f is equal j minus in the high-level language. You will write it in this way. If the condition allows one otherwise clause. So when the clause 1 is executed, we will jump the remaining part. From the emails and the statements in the emails, we will jump. But if the condition is not true, we will jump to the second part of the structure and else part will be executed. So in fact, we can write it in this way if condition is to go to L1 and to this path. Otherwise, we come to the next instruction and the class 2 will be execute and we will skip the class 1, skip the if part and come to this point. So this is the skip part that we should pay attention to it in the high-level language you only write if else, but you will know that when, if executed, the part will be executed. How? By jumping from them and come to the statement after the effort, if else structure. So this is the equivalent code or this high-level language. Assume that I am j are inside just 19 and 20 and if g are inside these registers 1670 918. First you check if I, Andre, are equal, French equal. If it is equal, jump to the label to this line. So if they are equal, the control will be moved to the true label. Otherwise, we come to this point. This point is this part, the start of the structure. So in the first part, I should compute the statement. If they are not equal, they come automatically to this part and we compute this statement and jump from the other part. To check it, this is the statement, the subtraction part, and jump from the if part. Statement of the if so if is true to the statement and the addition part will be execute the f equal the implement and we come to the exit. So we ignore this part because if is satisfied. but if it is not satisfied, this is the execute, and we should skip the if part, the statement of the if by this jump. So when you write a code in high-level language, the compiler automatically compare these labels into your MIPS assembly equivalent code. And by this way, your high-level language will be translated into the assembly.